In this video, we're going to look at how to evaluate trigonometric integrals that involve a product of powers of tangents and secants. The key to evaluating these types of integrals is to ultimately make a substitution, much like we did when we were looking at powers of sines and cosines, where one of the two powers were odd. And in this case, we want to make one of the following two substitutions. We either want to substitute u equal to tangent of x or u equal to secant of x, depending on the exponents m and n. In order to make either of these substitutions work properly, we need to isolate the derivative of the expression that we're letting u equal in each case, which means we need to either isolate secant squared of x, which is the derivative of tangent of x, or we need to isolate secant x times tangent x, which is the derivative of secant x. And so our first step in our solution process will be to isolate one of these two expressions. Once we isolate one of these two expressions, we can rewrite everything else in terms of either the tangent or the secant function, depending on which substitution we're going to make. And we can do that by using the trigonometric identity that says that the tangent squared of x plus 1 is equal to the secant squared. And so this will allow us to convert even powers of secant to powers of tangent, as well as by subtracting 1 from both sides, converting even powers of tangent to powers of secant. So let's take a look at a few examples of this process. In this first example, we're asked to evaluate the integral of tangent squared x secant to the sixth x dx. The first step is to isolate either a secant squared or a secant times tangent. If we attempted to isolate secant x tangent x, as shown here, what we would be left with is the tangent of x times the secant to the fifth of x. Since we've isolated secant times tangent, we would need to convert everything else to be in terms of secant, and that means that we'd have to have an easy way to convert tangent of x to secant. And there's no nice way to do this. The identity that we just looked at a few moments ago involves even powers of tangent. If we had tangent squared here, we could easily rewrite that in terms of secant, but there's no nice identity that involves just tangent of x and not tangent squared. And since we're not able to easily rewrite this in terms of secant, this tells us that this particular approach is not the right way to go about this integral. So instead, let's try to isolate a secant squared. If we try to isolate a secant squared, what's left is the integral of tangent squared of x, secant to the fourth of x times secant squared of x. And because we have secant squared of x as our isolated term, we want that to be du when we ultimately do our substitution. And so that tells us that eventually we're going to want to use u equals tangent of x as our substitution. And so we need to convert everything else to be in terms of tangent. Tangent squared of x, of course, is already in terms of tangent. But secant to the fourth, we can rewrite as tangent squared plus 1 quantity squared. So this was just secant squared of x raised to the second power, and then replacing secant squared of x with tangent squared plus 1. And of course, we want to multiply by our secant squared of x. Now we have our secant squared isolated, everything else is in terms of tangent, and so we're good to go with our substitution, u equals tangent of x. And of course, that means du is going to be secant squared of x dx, which we already have in our integral. And so here we end up with the substitution, the integral of u squared times the u squared plus 1 quantity squared du. And so now we have a relatively straightforward integral to compute in terms of u. We just expand out algebraically the integrand here. We find an antiderivative of that resulting function and go back to x by replacing u with tangent of x at the end. So picking up where we left off with the integral of u squared times u squared plus 1 quantity squared du, this becomes the integral of u squared times u to the fourth plus 2u squared plus 1. We then distribute the u squared and get u to the sixth plus 2u to the fourth plus u squared. Using the power rule in each term, we get the antiderivative here to be u to the seventh over 7 plus 2u to the fifth over 5 plus u cubed over 3, all plus c. And finally, we go back to x by replacing u with the tangent of x. So we get tangent of x to the seventh power, all over 7, plus 2 times the tangent of x to the fifth power, all over 5, plus the tangent of x cubed over 3, all plus c. And this is our antiderivative of tangent squared of x secant to the sixth of x. In this example, we want to evaluate the integral of tangent to the fifth of x times the secant to the 11th of x dx. If we try to isolate a secant squared, like we did in the previous example, we would end up with secant to the ninth power remaining and need to convert that to be in terms of tangent. And that's not possible since 9 is an odd number and we can only convert even powers of secant to be in terms of tangent. And so this tells us that isolating secant squared, like in the last example, will probably not work in this particular case. So instead, let's try to isolate secant times tangent. When we do that, the remaining part is tangent to the fourth times secant to the 10th, of course multiplied by secant tangent. And because secant tangent is the derivative of secant, we know that we ultimately want to do a substitution of u equals secant u, or secant x rather, and du will be secant times tangent. And this means that we need to convert everything else in our integral to be in terms of secant. In particular, we need the tangent to the fourth to be written in terms of the secant function. And so we can do this by remembering that tangent squared of x is going to be secant squared minus 1. And so tangent to the fourth will be that expression squared. Tangent to the fourth is tangent squared quantity squared, and tangent squared is equal to the secant squared minus 1. And then we're multiplying by secant to the 10th and secant tangent. And now we have everything that we need for our substitution. We can substitute u in for secant of x, and we get the quantity u squared minus 1 squared times u to the 10th multiplied by du. So as in the previous example, once we made this substitution, this became a relatively straightforward integral to compute. We just need to clean up our integrand algebraically, use the power rule to find an antiderivative, and then replace u with secant x to find our value for our original integral. So picking up with this integral, we're going to expand the u squared minus 1 quantity squared to get u to the fourth minus 2u squared plus 1. We'll then distribute the u to the 10th, and we'll have u to the 14th minus 2u to the 12th plus u to the 10th. And now we're ready to antidifferentiate this function using the power rule. So we get u to the 15 over 15 minus 2 u to the 13 over 13 minus u to the 11th over 11, all plus c. And the last step, as always, is to go back to the original variable. So here we get secant of x to the 15th power over 15 minus 2 times secant of x to the 13th power over 13 minus secant of x to the 11th power over 11, all plus c. And this is our antiderivative of tangent to the 5th of x, secant to the 11th x. If you would like to try some examples like these, pause the video and try to evaluate the integral of tangent cubed of x times secant to the 7th of x dx, and the integral tangent to the 8th of x times secant to the 4th of x dx. You can resume the video in a few seconds and see the full solutions for both integrals. For the first example, we're going to isolate a secant times tangent, which would then give us the remaining part of the integrand to be tangent squared secant to the 6th. We can convert tangent squared to secant by replacing it with secant squared minus 1, and then making a standard u substitution of u equaling secant x and du equaling secant x tangent x dx to get the integral of u squared minus 1 times u to the 6th du. We distribute the u to the 6th to get u to the 8th minus u to the 6th as our integrand. We antidifferentiate each term to get u to the 9th over 9 minus u to the 7th over 7, all plus our arbitrary constant c. And then lastly, replace u with secant x to obtain a final value of secant to the 9th of x over 9 minus secant to the 7th of x over 7 plus c. For the second integral, we'll isolate a secant squared of x, leaving a remainder part of the integrand to be tangent to the 8th of x secant squared of x. We can then convert this all to tangents by replacing secant squared of x with tangent squared of x plus 1. We can make a u substitution with u equals tangent x and du equals secant squared of x dx to obtain the integral of u to the 8th times the quantity u squared plus 1 du. We distribute the u to the 8th to give us u to the 10th plus u to the 8th as our integrand. And then we antidifferentiate those terms to obtain u to the 11th over 11 plus u to the 9th over 9 plus c. Going back to x, we get the final value for our integral to be tangent of x to the 11th power divided by 11 plus tangent of x to the 9th power over 9 plus c.